So let's start with the next round of lectures in our course, and this will build upon what we have learned so far. So let us just have a quick recap of what we have done so far. We have tried to understand computation of numbers. That means we want to actually deal with different values and quantities. So we need a proper representation system in order to depict those quantities and values which we want to work with. And we learned about all the popular number systems we have at present with us, and also the ways of dealing with signed numbers, and then the arithmetic operations related to normal numbers as well as signed numbers. So all these things we learned. Uh, so what we learned actually, to put it in precise terms, or if I want to say in one sentence, so we learned manipulation of numbers. That is what we learned. We learned how we can manipulate numbers to create new numbers. So this is what we learned. We learned various operations which we can perform on numbers, as well as we learned several sort of coding which uses the binary, the bits from the binary number. So as such they will look like binary words. However, they might not be might not be binary numbers. So they may look like binary words. So they are string of bits. So that is why it is a binary word, but it may not be a binary number, because if you evaluate that string of bits, what you will get is not what is actually encoded in that particular code. So such codes we also see, like the BCD, XS3, gray code, etc. So though they are utilizing the the bits from the binary number system, they are not binary numbers per se. So now going ahead, if we want to do computation or any operation on these numbers and codes, then first question is, what is the system in which we would like to do it. So if you had seen the one video I had shared at the very beginning of the course, if you have seen that video, you have understood that the binary number system gives us a power to implement computation in machines. That means the computation that we do in our mind, that same sort of computation on numbers, the manipulation of values, so this sort of things even a machine will be able to do if we utilize the binary number system, because we have in our hand the power of switches. So switches are something that we have in our machines. So these are physical things that we have with us. So we have mechanical switches, we have electrical switches, all sorts of switches are there. So switches are some basic physical elements with which we can work with, and they can come together. Many switches can come together to form a machine, and that machine may be utilized to do computation, because these switches in a way are also binary in nature. So they can either be on or off, and in a way they can represent the bits 0 and 1. So if we assign, so there is a sort of assignment that we have to do. If we assign the on state of a switch to the binary bit 1 and the off state of a switch to binary bit 0, then we have a particular system of assignment, and that system is called as positive logic system. So in positive logic system, it is very straightforward to us that when something is on, thus when the switch is on, we assign the binary bit 1 to that particular state of the switch, and if the switch is off, we assign the binary bit 0 to that state of the switch. So in this way, if we use binary numbers to manipulate, if we use binary numbers to work with values and quantities, do computation, then that pen and paper computation that we will do with the binary numbers can be done by a physical machine as well. And then what we gain is that we don't have to spend that effort doing the pen and paper calculations. We can directly give that problem to the computer, and the computer will be able to solve that problem. Additionally, what happens? Additionally, all those codes, etc., which we made using the binary bits, those codes, etc., can also be processed in that physical machine. Those codes, etc., can also be made and processed within that physical machine. So this sort of a physical machine which is able to do computations on numbers, that physical machine is called a computer. In the computers that we are used to seeing, most of them, and I'm sure you have not come across any computer which is not using the binary number system or not using the concept of bits in order to do the computation it is asked to do. So all the computers that we have seen are utilizing the binary bits, the binary number system, the binary words, in order to do something, in order to process the data given to it, to manipulate the data given to it, to do computations on the data given to it. So the computer is dealing with binary bits as such. So all that thing could have been done on pen and paper by human beings, but they would have taken a very long time, and that's why this is called a machine, because it eases, or it makes the time required to do such operations very less, and the effort required to do those operations is nil for a human being now. And the computer, which is that physical machine which can work with the binary numbers, is now able to do that work for us. What is important is that we are using switches in this physical machine. So this is important to understand. What we are basically using in these machines called computers are switches which can have two definite states called the on and the off state. So the switch can only be on or off. So those sort of switches can be used to denote the 1 and 0 of binary bits, and we would be able to work with the binary numbers and words. Now there is another assignment that is possible, in which the switch on state is represented by 0 and the switch off state is represented by 1. that is called the negative logic. So here you see the 1 is represented by 0 and the 0 is represented by uh, the off state is represented by 1 and the on state is represented by 0. So this is the negative logic. So both these logic systems can be used when we are using the computer. See, the computer is only switching on and off the switches. What after that is our interpretation of the states of those switches. So if we interpret through positive logic, we will be interpreting the switch on state as 1 and off state as 0 and will get some result. If we are interpreting using the negative logic, we will receive exactly opposite sort of result, because we will be interpreting on state of the switch as 0 now and off state of the switch as 1 now. So exactly opposite result we will get. So it depends on what assignment we have done in order to work with the machine. Normally, usually we are doing the positive logic. We are assigning the positive logic and we are working with the positive logic when we are working with the computer. Unless it is otherwise stated, you should always assume that you are working in the positive logic system. Now, when we understand that we are able to move to a computer or this is a physical machine which is called a computer, and the basic component of the computer will be switches. Now just a word of caution, at this moment I am only talking about switch. I am not talking about whether they are mechanical switches or electrical switches or what. So I am only talking about switch. So just the idea of switch is important, that it can have two definite states, one is on and one is off. So this idea is inherent to all of us and we can go ahead with it. So when we have the physical switches in a machine, then they need to be in a machine. What happens? These elements are connected in some way. So the physical entities can be either connected in series or in parallel. So these switches in a machine are either connected in series or in parallel, as you see in the diagrams. So if we are connecting in series, here if we are connecting in series, you can very well understand that unless both the switches are on, a signal will not pass through these switches. That means that the total circuit will not be considered as on unless both the switches are on, both the elements are on. Similarly, in parallel, if any of these switches is on, then the entire connection can be considered as on. I hope this is very clear to you. So this is the two different types of working that happens when we connect switches in series and parallel. And please note, there is no other possible ways of connecting two switches. Okay, so when we do this, the series connection works as if like a logical AND. Logical AND means if two things are true, then only the total thing is true. So if A is true and B is true, then the entire thing becomes true. So that is the logical AND. If both A and B are true, then the entire thing is true. So that is what you see here. If both the switches are true, or you can say on, the entire thing is true or on. In OR logic, what is logical OR? If either A or B is true, then the entire thing is true. So if either A or B is true, then the entire thing is true. That is logical OR. So here you can see this parallel sort of connection is like a logical OR, because here if any one of these switches is true or on, then the entire thing is true or on. So in that manner you can understand that this is logical and this is logical OR. When we are actually dealing with positive logic system, that we need to understand, because on we are referring as true here, and off we are referring as false. So same as on we had referred as 1 and off we had referred as 0. So here also on we are referring as true, and almost we have an idea that true is like 1, and when it is false it is like 0. So this is also one system of assignment. This is also the positive logic system when we are working with. Then the series connection is logical and the parallel connection is logical OR. And this would be actually the exact opposite when we are working with the negative logic system. So then what happened is this, that the connection of the switches that we can do within the computer, this connection of switches is basically taking the shape of logical and logical OR operation. This connection of switches is basically taking the shape of logical and logical OR operation. So we have to actually, when we are working with computers, we have to understand how the logical and logical OR operations manipulate the various logical elements on which they are operating. That those A and B that I am saying now, that both A and B have to be true, so that this logical and, so that the output of the logical and has to be true. So what are these A and B? So they can be any statement, they can be anything actually, and all this actually, all this manipulation using logical and logical OR operators are taken care by a system which is known as Boolean algebra or binary logic system. So binary algebra or Boolean algebra, Boolean means binary. So the Boolean or binary logic of and or is dealt with in a system of algebra, in a mathematical system. So algebra is basically a mathematical system of manipulation of the elements in that system. So Boolean algebra is a system which is able to manipulate the elements within that system using the logical operators and or. There are logical operators defined in this algebra, not arithmetic operators. We know arithmetic operators. We know that arithmetic operators are like this plus, minus, all these things. So plus, minus, multiplication, division, these are arithmetic operators. So we are not talking about arithmetic operators in Boolean algebra. In Boolean algebra we are talking about logical operators and or logical operator. And there are elements like in normal algebra, you have elements like scalars a, b, etc. Here also we have elements, we have logical elements a, b, etc. And the logical operators are acting on these elements of that algebraic system, whereas in normal algebra the arithmetic operators are acting on these elements of the normal algebra. So if we were dealing with real algebra, then a, b would be real numbers. real quantities. If we were dealing with complex algebra, then a, b, this small b would be complex quantities. When we are dealing with Boolean algebra, these a and b are logical quantities. Okay, so we have to understand these sort of differences. So what happened here is that we are trying to understand the manipulation of the switches using the system of Boolean algebra, and then what happens, the mathematics that we are able to perform in the Boolean algebraic system, that mathematics gets a physical shape, or that mathematics gets a uh, mm, we are able to reproduce that mathematics in a physical environment of the computer using the switches. So that is what happens. So the mathematical operations with the Boolean variables now corresponds to operation of switches connected in the computer in some network. So the entire mathematical operation using the Boolean variables, so the operation would be using AND or this sort of logical operators. That same thing would be like a network of switches in the computer. That is how we are able to understand what operation is happening within the computer, or if we say it in the exact reverse way, if we know, or if we understand a sort of operation on Boolean variables and wish to implement that operation in the physical computer, we would know what sort of connection of the switches we need to do so that this operation is able to be implemented in the computer. Because we know that in the Boolean algebraic system the operators are AND OR, and for each AND OR this sort of things we know the exact connection of the switches that we need to do. So for a mathematical expression using AND OR etc., these operators, we would be able to construct the circuit or the network of switches in the computer, and that particular mathematical operation would be physically implemented, and we would get the result also. The result we will be able to extract from the physical machine. So this is how the physical machine will be able to do something which is abstract in nature. So the mathematics is abstract in nature, but the physical machine would now be able to do this abstract mathematics, which was thought to be beyond the realm of machines. Abstract operations, calculation, computation of numbers, doing mathematics, these were thought to be beyond the capabilities of machines. They were thought to be only the only a human capability. But then these machines were invented, as you had seen the story in that video that I had sent. These machines got invented, and these computations, these abstract operations that were done only by human brains before, were now being able to be performed using machines as well, physical machines as well. We need to understand this fact, and also like uh, take some moment in order to reflect on this fact and realize the great importance of this invention. So this was a paradigm shift in the history of inventions. So previously inventions were done in order to reduce the physical labor of humans, or to make the life or lifestyle better, or or more easier to live. This sort of things, inventions were directed on those directions. Now suddenly there came a possibility to even reduce the mental effort which was getting spent on many things. So these computations and all other different things, so the mental effort could now be given to a physical machine. So this was a paradigm shift in the history of technology, and you know what great revolution it had brought about in our human civilization. And in the heart of it lies the use of binary number system, and the use of Boolean and the mathematics of Boolean algebra, and the simple way, the very simple invention which led to a very tremendous change in the human civilization. So the simple implementation of this Boolean algebra using connection of switches, that's all. And then people made it more complicated or more efficient and more capable. All these things have been going on and people are doing it, but at the heart of it all, this is what lies. So we need to have a feeling of this, of the greatness in this invention. So if we have to now go ahead and understand how the computer works, we have to actually learn a bit about Boolean algebra. We have to learn a bit about Boolean algebra. So let's go into it. So as any algebraic system works, one has to define the objects in that algebraic system and the operators in that algebraic system. Along with the objects and operators, we have to assume some fundamental things. These are called fundamental assumptions. These are actually fundamental relationships, operating relationships, which we assume between the objects. So these are fundamental operating relationships between the objects which we assume beforehand. So we begin with these things, with these assumptions, and these assumptions are called axioms. So in any algebraic system, the algebraic system is laid down with objects, operators, and axioms. These three things are there. Someone who is inventing the algebra would give you the objects, operators, and axioms to work with. With these three basic things, all other computational relationships or operating relationships within that algebraic system means using those objects and the operators, can be actually discovered. So the algebra takes shape. The discovery of different mathematical truths related to that algebraic system is brought about. So let us look into the objects and operations defined in Boolean algebra. So in Boolean algebra, there are only two objects. So the variable space, so these objects are the variables which are there in the Boolean algebra. So this variable space consists of only two objects. One of the object is 0 and the other is 1. Only two objects, 0 and 1. Please think of 0 and 1 as objects now, not as numbers or digits. Just think of them as some object, something. So in place of 0 and 1, you could denote them as any other thing that you would wish to denote them with, maybe a square and a triangle. That would also be fine. Okay, but since we are so used to working with numbers, seeing digits, etc., we represent one object as 0 and the other object as 1, but they could be represented with any symbol. Please understand this. So the variable space we represent with 0 and 1, there are only two objects, and we define some operations on these objects. We say that if x is a variable, then x can take either one of these on one of these objects. So x can become one of these objects. So if x is the object 0, then x is not the object 1. That is what it is saying. So if x is the object 0, so it says that x is the object 0 if x is not the object 1, and vice versa. That means x is the object 1 if x is not the object 0. So I will not keep on saying object 0 and object 1. I will start saying 0 and 1. This is how we actually say things, but at the back of our mind we should remember that these are just some objects. Okay, so that is all. They are just some objects which we call as 0 and 1. So now the next relationship is like this. So if x is 0, then something called the x complement is defined. This is the x complement, written as a dashed, x dashed is 1 and vice versa. So we have an understanding of complements coming from the number systems, and here also you can see that the complement is almost the same. So it is just the other thing. So it is just like in binary system it was flipping of the bits. Here it is also like flipping of the objects. So if x is 0, then x complement is 1 and vice versa. Operations defined here are logical AND and logical OR. They are not addition, subtraction, multiplication, division. They are logical AND and logical OR. But always we would not be writing. So suppose we have two variables x and y, two Boolean variables x and y, and we wish to do an AND operation. So we have to write like this. We have to do an OR operation. We have to write like this. So we don't want to write so many things actually. So to do the shorthand, what we did, we represented AND by this symbol dot, and we represented OR by this symbol plus. But please pay attention that this is not multiplication, this is logical AND operator. When you are in the purview of Boolean algebra, this is AND operation. The dot represents AND operation. So this is A and B, where A, B are Boolean variables, can be 0 or 1, B also can be 0 or 1. Similarly, this is not A plus B but A or B. So please pay attention to this and don't mistake saying this as AB or A plus B. So this is called as A and B. This is also called as A or B. So it is in our practice to call this as dot and call this as like AB or A plus B. But even if you sometimes by mistake, or even if I sometimes by mistake call this as AB or A plus B, you should automatically translate it in your mind as A and B and A or B. Okay, so this is what caution I am putting forward at the very beginning. So I try my best to speak of this symbol as A and B and this symbol as A or B, and most of the times I am good with that, but sometimes I may miss speaking it in the correct manner, but you should understand it in the correct manner. So that is what I want to stress here. So now the axioms, the operating relationships, the axioms are these, that if you take the zero object and do a logical AND with the zero object itself, it will give you the zero object back. So 0 and 0 is 0. That is the first axiom. So it seems very obvious that 0 and 0 would be 0, but please consider that 0 here is not a number, it is an object. So when you are introducing an object, you have to also introduce the operating relationship between the objects. That's why axioms are important. So even in usual number systems, this sort of introduction was made in order to understand what is the addition operation and what is the multiplication operation. So we, if to have an idea of what is addition and what is multiplication, this sort of definitions were given in the normal algebra also. Here also we have to understand what is the logical and logical or operations. For that we have to define these relationships. So the definition goes in this way, that 0 and 0 would be 0, 1 or 1 would be 1. This is the definition of these logical and logical or operators actually. So if you AND a 0 with a 0, you are going to definitely get a 0, and when you are doing a OR operation with 1 and 1, you are going to get a 1. Similarly, 1 and 1 will also give you a 1, 0 or 0 will also give you a 0. 0 and 1 will be same as 1 and 0, and that will also give you 0. 1 or 0 will be same as 0 or 1, that will also give you 1. Now these are very simple to remember, so no need to stress so much on this thing. Just have an idea that these are not basically numbers but objects, and the relationship between them are like this. So after we have understood the axioms, then comes the level of theorems. So these are certain truths based on these axioms which we discover. These truths we discover in the purview of the algebraic system that we are working with, or the mathematical system that we are working with. So in case of Boolean algebra also there are certain theorems, and we need to understand this, what are these theorems. So in all these theorems you see that a name has been given, a statement has been given, and a dual has been mentioned. So there is always a dual of each of these theorems. The dual you will not understand straight away. At the very end we have a duality theorem also. So when we go to the duality theorem, you will then appreciate this column of dual. Okay, but let us now read through and understand. The identity theorem is very straightforward. It says that any element, any Boolean variable when ORed with 0 gives back the same variable, and when ANDed with 1 gives back the same variable. This is what it is saying, the first statement. Null element means this variable when ORed with 1 gives back 1. That means it is as if that variable was not even present there. So a variable when ORed with 1 gives back 1. So as if the variable was not even present. And similarly, when a variable is ANDed with 0, it gives back 0. Now to verify all these theorems, if you are asked to verify these theorems, what you can do, you can verify for both the values that are available for this variable. you can have only 0 or 1. So you use 0, you establish that the equality holds. Then you use 1, you establish that the equality still holds. So the equality holds in general for the variable x. So in this way you have to verify, and for showing those equalities holding you have to take help of these axioms which are defined. So unless these axioms were defined, were given to you, were assumed to be fundamental, you would not be able to establish these general truths on this algebraic system. Please keep that in mind. So the null element is understood. Idempotency means if you operate a variable with itself, it gives back the variable. So this is a very important theorem which is I think is one of the distinctive attributes of Boolean algebraic system, idempotency. This is not present in normal algebra. So if a variable is operated with itself, then it gives back the same variable, and this operation can be both and or. Involution, if you take complement of the complement, you get back the same variable, that is involution. Complements, the theorem of complements says that if you do an operation, if you do a or operation with the complement, you get 1. If you do a AND operation with the complement, you get the object 0. Commutativity says that the OR operation as well as the AND operation are both commutative. That means the order of doing the operation is irrelevant, the answer would be same. You see, the order of doing the operation is irrelevant. Associativity says that if there are 3 variables with which you are doing the operations, you can take any 2 variable first, do the operation, and then take the 3rd variable. It would not hamper the result of the operation. That is what it is saying. As you can see, you can do xy first or yz first. I'm not saying the and. You can do x and y first or y and z first, and then do the second AND operation. The result would be same. Similarly for the OR operations. Distributivity says that the OR and the AND can be distributed over each other. Now this statement basically means what is written here. So your x and y or x and z is x and y or z. So if you read it in a dot and plus way, it is very evident, right? But this one would not be evident. The dual statement is not evident in the normal multiplication and addition scenario. This happens in and or scenario only. So here it says x or y and x or z is x or y and z. Okay, so this you can have a simple proof also of this. So I hope this is not required to be proved, but this can be proved. The LHS actually, if you open the brackets, it is x and x plus x and z plus x and y plus y and z, and here this is x and this is okay. So this is a theorem. I think one can do the proof by using the 0 and 1. So you can put 0 and 1 in all these cases, and you can see that both sides would be coming to be equal every time. For every combination of 1 and 0, both sides would be coming to be same. So in that way you can prove this statement, this dual statement. Now the next set of theorems, the first one is the covering theorem. Very interesting that x or x and y is x. This is the covering theorem. This is very simple to prove actually. If you take x common, you will have 1 or y, and 1 or y is 1, so you get x. Similarly here x dot x or y will be equal to x. So here in the same manner, I guess here you can do x plus x. And take here you are taking x as common and you are getting 1 plus y. And this comes actually from the dual. There is a theorem of duality, but also you can prove this by I'm not remembering exactly the way it can be proved, but you can always prove by using the values of 0 and 1 in either of these variables and see that what is coming out as a result. So if you have x and y, so you can do this sort of a thing. You have x and y, you have all these possible combinations of values that are possible, and you evaluate the left hand side, what you will get as a result. So if this is a result in the right hand side, what you will get will basically be same as x, so in that way you will be able to prove these statements. So here in the next one is combining. Here what happens, this is also very easy to see, that x and y plus or x and y dash would be x. So if you take x common, it is very easy to see why this happens. Similarly here, this is the dual statement, x or y and x or y dash is equal to x. So that is the dual statement. So what is to be seen here is that if you have a operation where you have both and or, and you have one variable as itself and another variable complemented, then the result is that variable which was not complemented, which stays as itself in the two expressions, in the two terms. So here there are two terms, here there are two terms, and it is related through some or and operations. So this, in these two terms, if you have a term which does not change and another term which is complemented, then the result is that term which does not change, is that variable which does not change. So it is like that. Similarly, covering also you can read it in that manner actually. So if you have a variable, only a one variable and another term with that variable and some other variable or even a function, this y could be actually a function also, then what you get as a result is the single variable that we had. Here also, the single variable will come out as a result, because the other term which is ended with it is that variable plus some other term. So this term gets neglected, basically only this variable comes out. Consensus is very important. This is very important. Let me highlight this. This is very important. Consensus. So in this what happens, there are, you see there are three terms to begin with and one term is vanished. This term can be vanished. What is this term which gets vanished? You look at these terms. You have a variable x in one term and its complement in the other term. In place, apart from x, there is some other term associated with x. Apart from x complement, there is some other term associated with x, right? So these two terms which are associated with x and x complement, these two terms come together to form the third term. So when this sort of a thing happens, then this third term can be struck off. then this third term could be struck off, and this happens also for the AND relationships. These are the OR relationship, this is the AND relationship. So x or y and x dashed or z and y or z, this y or z now can be eliminated. So pay attention to the consensus theorem. This is very useful because it straight away removes one term. Now there is the generalized idempotency, which I hope you can very well understand what we are doing here. This is x or x or x or x n times. So no matter how many times you do, you will get x. And similarly, if you do the AND operation with itself, no matter how many times you do, you will get back x. De Morgan's theorem is another very important theorem. De Morgan's theorem. Here it says that if you do if you have n variables, you AND them together and then take a complement, it is same as ORing the complements of the variable. It is ORing the complements of the variables. You see, the OR and AND operation are written as pi and sigma, normal sum and product sort of thing, but they are OR and AND operation. So it is like for two variables I will show. So what we are saying is x1 dot x2 and x2 complement will be x1 complement or x2 complement. That is what De Morgan's theorem is saying, and this is for any number of variables. So there can be n variables here, there would be n variables here. The dual statement is also true. So if you have x1 or x2 complement, it would be x1 complement and x2 complement. This you should remember always. This should be by hearted by you. So you should remember by heart this De Morgan's theorem. Generalized De Morgan. So this is simple De Morgan. What does generalized De Morgan say? Generalized De Morgan says that if there is a function, any function, so here the function was simply a term with AND operators, simply a term with OR operators, but a general function can be there with OR and AND operators. Like suppose you have a function like this, where both and OR, all these operators are there, and it can be a lengthy term as well, lengthy function as well. So I am taking as an example only these two terms, and now I do a complement. Then what will happen? My variables will be complemented. You see, you read it, the variables are getting complemented, OR is getting replaced by and is getting replaced by OR. That is what happens. So what will happen here? We will have x1 complement or x2 complement, and this would come together because these were together to begin with. So in the result also these will come together. So the bracket will come. Unless you give the bracket, your result will be wrong. Please remember this. And then a AND x3 complement. This is the result of generalized De Morgan. So if you have a expression where you have a complement, then you first simplify that expression using the generalized De Morgan's rule. There is another rule. This is not so useful all the time, but what does it say? If you have a complicated function of n number of variables, this is same as taking the variable x1 out of this function, ORing with the function itself, replacing x1 with 0, then ANDing with another term where you have x1 complement taken out of the function and the x1 term replaced by 1. That is what it is saying. So maybe what it is says, so if you have, let us try to give an example, x1 x2 plus x3, this is a function. This would be what they are saying, this would be same as x1 or you have to write down the function again, replacing x1 with 0. So you have only x3. Then you have to AND with x1 dashed, and then you have to write down the function again, and you have to replace x1 with 1. So you would get x2 plus x3. And if you had chosen, suppose, x2 as the variable to be taken out, you could have taken x2 out as well. So it would be x2, then you have to replace x2 with 0, so you get x3, then x2 dashed, and you have to replace x2 with 1, you would get this. Similarly, you can do it for x3 also. So you take x3 out, and you see you would get this, and then x3 dash plus, actually you are getting x1 x2 plus 1, and this is 1, and you are getting back the same expression actually. So that is what you can see. So this works. The next and the final statement is the duality theorem. And the duality theorem says that the dual of a function, so this signifies the dual of the function f composed of all these things, would be equal to the same function where you don't change the variables. See, you don't change the variables. What you change? You only change the or and AND operators. That's all you change. So if I want to write, suppose I want to find out the dual of, if f is so I will show you one very important relationship also. I guess that was not covered in these things. Yes, so there is a relationship which is this x plus, sorry, let me write it with another color. There is a very important relationship which is this x plus x dashed y is x plus y. You see that this type of relationship is not covered in any of the theorems, but this is a very useful relationship and we use it a lot of times, and this can be very easily proved with the concept of duality. Suppose f is x plus x dashed y, then your fd, what would be fd? Fd would be x dot x dashed plus y. Only or and AND operations have to be interchanged, nothing else. And then you expand this, what you will get, the first two would combine to give 0, and the result would be x dot x and y. Now the original f would be dual of this again. So original f would be dual of this, which is x or y. So you get the right hand side. So in that manner you have proved that this expression is valid. So you remember this expression always. This is very useful in solving problems or minimizing expressions. And now when you have understood the dual theorem, you can appreciate the dual statements. Look at all these dual statements. what we have done? Nothing, only altered the or and AND operations. That's what we have done in all the dual statements. And or operators are interchanged. Yes, another thing has been interchanged, which is the 0 and 1. The 0 is interchanged with 1, the 1 is interchanged with 0. So actually in this statement, this should also be written that maybe 1 comma 1 0, and here comma 0 1 would be written. So the 1 changes to 0 and the 0 changes to 1. This also happens in duality. So now we use these theorems in order to simplify some expressions. So we learned these theorems. So let us utilize our learning to solve or to simplify two expressions here. So a plus a or b and c, this entire expression. First thing what you would do, you would open up this. Okay, first thing you open up any expression in brackets. So this is like the generalized De Morgan's. So your result would be this a dashed dot b dashed plus c dashed, right? So a dashed b dashed plus a dashed c dashed plus all these things plus ad plus a dashed c, and these two I will combine. Which two I have combined? A dash c plus c dash d a dash a. Yeah, so this and this I have combined. So this and this you can combine, and you see that what you will get, you can take a dash c common, and you will get d dash plus 1. So that would give you 1 only. So you can basically, this term does not remain in the second line. So this is what you get. So you should so let me write in the proper manner so that you also do it in the proper manner. So you should write c dot d as a dash c dot 1 plus d dash, and in the next line you can remove this. So in the next line, then in the next line, actually I can take a dashed common. Yes, I can take a dashed common, and I will get b dash plus c dash plus c, right? This had already become 1. So we have a dash b dash a dash c dash a dash c, like this. Then I have b dashed d plus c dashed d plus ad. So all these terms I am noting down. Now this c dashed or c combines to give 1, so this becomes a dashed. So this becomes a dashed. Then you can actually have this taken together, then this, and then this. Now you look here, a dashed or ad, this will give you a dashed or d plus b dash d plus c dash d. So why this is happening? Because x plus x dash y is x plus y. That is why. So this we already proved using the duality statement. Then you can take D common, and when you take D common, you get 1 plus B dashed plus C dashed, and that gives you A dashed plus D. So you see this long expression can be shortened to get this final expression. Another one we will do very quickly, and here there are no brackets to be opened. So what we would do, we would first look for consensus theorem, if consensus theorem could be applied. So that is what we will first look at. So here, so consensus theorem means that I would look for terms where I have the one term and another dash term and another term where the other two terms are combined together. So you see here that in these three terms you have A here, A dashed here, and the remaining terms are combined to form this third term which can be cancelled out. Again, in these last three terms you have D here, D dashed here, A and B comes together to form this term which you can cancel out. So what you get is this. In the next step, you can combine. For D you can combine, let us do this. A we can combine with B and C, these two terms you have B D dashed, and then you can take D common, you get A or A dashed B dashed, that means you get A or B dashed, and then you have a D. So you get this term. So you can also take A common from here, you get B or C or D, and then you get B D dashed or B dashed D. I think I missed the BC term. Yes, you get a BC also. This is the simplification. So with this I end the lecture, and we will look up into all these things. We will go further in the next lectures. So thank you for your attention.